All right, ladies and gentlemen, we are going to talk about electric potential. Capacitors are use a lot of electric potential, and capacitors exist everywhere. Nature has evolved nerve cells of which the axons are capacitors of a sort. By creating a capacitor cell membrane and electric field between the surfaces of the cell membrane, we are able to store energy in electric fields for later use. We transform that energy in the electric field into energy of motion, and that's actually how we move and do different things. Notice that little monkey up here, he has to force this positive. He has to do work to make this positive go over here. If he lets go of it, that goes away. So that's going to talk about a lot of our electric potential. So work and energy. We've talked about these concepts in mechanics already. Okay. Energy comes for gravitational potential energy, just as mass times gravity times height. And that is created because of the gravitational field. So we have a gravitational force because of the gravitational field. All right. Then we are able with that force to create that force through a displacement is energy. So electric potential energy is um, a charge through a voltage, okay, or an electric potential. So remember that there's a force that causes on a charge in an electric field, and so that force on a charge is going to create our electric energy. Okay, and really voltage is just a force power that is put with a charge. So it's actually it's a field and a distance, really, is the way to think about it. It's a field and a distance, all right, on a charge. So gravitational work and energy. Work is done against gravity to move a block up a vertical height. So work is force times displacement or mass times gravity times height. The external force does positive work. The gravity does what we call negative work. We don't have to do anything to it. If we have to supply the work, it's called positive work. But if the field does the work, it's negative work. So the external force against the gravitational field increases the potential energy. If released, the field gives that work back. So electric potential energy is the same thought. Electric potential energy is the energy contained in a configuration of charges. So like all potential energies, when it goes up, the configuration becomes less stable, like us picking a block up off the ground. When it goes down, the configuration becomes more stable, just like when we let the block go and it goes to the ground. So electric potential energy increases when the charges are brought together into less favorable configurations. So when like sign charges get closer together or unlike charges get further apart. Now, electric potential energy decreases when charges are brought into more favorable configurations. So when like charges are getting further apart, then that potential energy decreases. And if unlike charges are allowed to get closer together, then they are actually going to decrease their potential energy. So work must be done on the charge by an outside force to increase the electric potential energy. Work done on the charge to increase electric potential by an outside force. So work changes the potential energy. When an outside force is applied to a positive test charge to move it a distance, the electric force does negative work and the potential energy has increased. And U is positive, okay, because we actually moved it closer. So we had to do work against the field. If a negative charge moves upwards a distance, then the electric force does all the positive work, and the change in the electric potential energy is negative. So it actually decreases as we go this direction, because that's the way it's going to go anyway. And the movement is created by the electric force. Now, electric potential and potential energy. The change in potential energy is directly related to the change in voltage. Okay, so our U, our change in U, is equal to our electric potential energy, which is equal to our Q times our change in V. All of these things, we know our U value, our U units are joules, our Q value is coulombs, and our V value is voltage, so volts. All charges will spontaneously go to a lower potential energy if they are allowed to move. It's just like diffusion. It goes from high to low. So this will instantly go from a high potential to a low potential if they are allowed to move. They will do it naturally. Since all charges try to decrease their potential energy and become less chaotic, then our U equals Q times V. And this means that the spontaneous movement of charges results in a negative U. Positive charges like to decrease their potential, so negative charges like to increase their potential. Since the electric force is F equals QE, the work that the electric force does as the charge moves from point A to point B depends on the amount of the charge. It's useful to express this work as a per charge basis. So work over charge equals the change in potential energy over charge. So that work value is actually known as our V value or our voltage. So the work done on charge is actually our voltage or our electric potential. So electric potential or voltage is defined in terms of the work to be done on a charge to move it against an electric field. So 1 volt is also equal to a joule per coulomb. So when we're talking about electric potential around a sphere, for a spherical or a point charge, the electric potential can be calculated by doing our U equals KQ1 Q2 over R, or our U equals V times Q. Okay, so we can do also V equals KQ over R. So these are lots of different ways to put these formulas together. They are all on your formula chart. So our V equals KQ over R would be a simplified or a rearranged version of putting our substituting our U equation of our KQ1, Q2 over R into our V equals Q over Q over, U over Q formula. So an equipotential surface is a surface on which the electric potential is the same everywhere. All right, this is a really important concept to understand. So if we have our charge Q here, then D is a certain distance from it, and it's on a circular path around that. Whereas A, B, and C are on a separate path, but they're all the same distance from Q. So that would mean that A, B, and C all have the same potential. So it really is to think about a circle. And so that potential is KQ over R. Okay, so that R value is where we're coming up with that electric potential or that voltage. So what happens to the potential as you move away from the charge point? This gets larger, so overall this gets smaller. So it decreases. So the electric potential decreases as you move away from the charged particle. Lines of equal potential are always perpendicular to the electric field lines and point towards the decreasing potential. So as we go out, it's decreasing, and these are perpendicular, notice, right here to the equipotential surface. So these are our electric field lines going away from our positive charge, and then we have our electric potential or equipotential surface, which is perpendicular to those lines. So field and equipotential lines are for a set of parallel plates, looks like this. So we have our electric field going out of the positive and into the negative, and we have our equipotential at 90-degree angles crossing those electric field lines. Highest to lowest. All right. I'm going to stop this as my part one, because that's about 10 minutes of our electric potential and electric potential energy. Look for our second recording for this information as well.